Before a star can become a brilliant, raging furnace, it must first be a cloud of unimaginable cold and darkness. The story of a star's birth isn't one of a sudden, fiery explosion. It is a quiet, patient, and million-year-long story of a slow collapse, a story of gravity quietly, relentlessly winning its long game. Let's begin our journey tonight in that cold, dark, and surprisingly beautiful stellar nursery. When you look up at the night sky, you see the brilliant, finished products, the stars. But the real work, the quiet, slow process of creation, happens in places that are almost completely invisible to our eyes. It happens in the vast, dark, and incredibly cold spaces between the stars. This is where we find the raw material for new suns, the structures known as giant molecular clouds. Let's just take a moment to appreciate the sheer scale of one of these clouds. It is a structure so vast that our human minds can't really hold it all at once. A typical giant molecular cloud can be hundreds of light years across. Remember, a single light year is about 9.5 trillion kilometers. So these clouds can stretch for quadrillions upon quadrillions of kilometers. If you were to place our entire solar system out to the orbit of Pluto inside one of these clouds, it would be like a single grain of sand lost in a fog bank the size of a continent. They are colossal. And they are incredibly massive. A single cloud can contain hundreds of thousands or even millions of times the mass of our own sun. But this mass is spread out over such a huge volume that the cloud is actually a near-perfect vacuum by earthly standards, far emptier than any vacuum we can create in a laboratory. It is a cloud of almost nothing that, through the patient magic of gravity, will eventually give birth to everything. The second defining feature of these giant molecular clouds is their incredible cold. The temperature inside one of these clouds is typically only about 10 to 20 Kelvin. That is just 10 degrees above absolute zero, the theoretical point at which all atomic motion ceases. It is one of the coldest environments in the entire universe. And this extreme cold is absolutely essential for star formation. In a warmer cloud of gas, the individual atoms are moving around too quickly. They have too much thermal energy, creating an outward pressure that resists the pull of gravity. But in these frigid, quiet clouds, the atoms are slow and sluggish. This allows the gentle, persistent, and incredibly weak force of gravity to finally begin its work, to slowly start pulling the gas and dust together. And what is this gas made of? For the most part, it is the simplest and most abundant element in the universe, hydrogen. But it's not the atomic hydrogen we usually think of. It is so cold in these clouds that the individual hydrogen atoms have been able to find each other and pair up, forming molecular hydrogen, or H2. This is why they are called molecular clouds. This molecular hydrogen is the primary fuel for the new stars that will be born here. But it's not just gas. Mixed in with the hydrogen and helium are tiny, microscopic grains of dust. This dust is made of heavier elements like carbon and silicon, which were forged in the hearts of previous generations of stars and then scattered into space when those stars died. This dust makes up only about 1% of the cloud's mass, but it is absolutely crucial. These tiny dust grains act like a shield, protecting the interior of the cloud from the light of nearby stars and allowing it to stay cold. And they also act as tiny meeting places, catalysts, where the hydrogen atoms can more easily find each other and form molecules. It's a quiet, cosmic teamwork between the simplest gas
and the dust of long-dead suns.
For most of its long life, a giant molecular cloud can exist in a state of quiet, stable equilibrium. The inward pull of its own weak gravity is perfectly balanced by the slight outward push of the gas pressure within it. It will just drift silently through the galaxy for millions of years, a vast, cold, dark, and patient cloud of potential. It is waiting for a nudge. A stable cloud will not collapse on its own. Something needs to happen to disturb its quiet balance, to give gravity the advantage it needs to start the process of starbirth. This brings us to the trigger for collapse. And the universe has a few different ways of providing this gentle, or sometimes not so gentle, push. The most dramatic of these triggers is a supernova shockwave. Imagine a massive star, which has lived its short and brilliant life in the vicinity of our molecular cloud, finally runs out of fuel and explodes as a spectacular supernova. This explosion sends a colossal shock wave of energy and material racing outwards through space. When this shock wave slams into our quiet, stable molecular cloud, it acts like a giant cosmic snowplow. It compresses the gas and dust, creating regions of much higher density. And in these newly compressed regions, gravity is now strong enough to overcome the gas pressure, and the process of collapse can begin. In this way, the death of one generation of stars can directly trigger the birth of the next. It's a beautiful, violent, and self-perpetuating cycle of creation. Another, slightly gentler trigger can be the very structure of our galaxy itself. Our Milky Way is a spiral galaxy, and the spiral arms are not just pretty patterns, they are slow-moving density waves. As our molecular cloud, in its long orbit around the galactic center, passes through one of these dense spiral arms, it gets squeezed, just like cars bunching up in a slow-moving traffic jam. This gentle, large-scale squeeze can be enough to trigger the collapse of the densest parts of the cloud. Finally, the trigger can come from the cloud's own new children. Even within a large cloud, some regions might collapse on their own and form a few massive, hot, blue stars. These new stars will immediately begin to produce powerful stellar winds and intense ultraviolet radiation. And this energy will push outwards, creating an expanding bubble of hot gas. The edge of this bubble acts like a shockwave, plowing into the surrounding cold, quiet gas of the parent cloud, compressing it and triggering a whole new wave of star formation. This is a process called sequential star formation, where the birth of one set of stars sets off a beautiful chain reaction, creating a new generation of siblings right next door. Whatever the trigger, the result is the same. A quiet, stable cloud is pushed over the edge, and the long, slow, and irreversible process of gravitational collapse begins. This is our next great chapter in the story of a star's birth. The initial collapse doesn't happen all at once across the entire giant cloud. Instead, the cloud begins to fragment. The densest knots of material, the parts that received the strongest push, begin to collapse in on themselves, separating from the larger cloud. A single giant molecular cloud will typically break up into dozens or even hundreds of these smaller individual collapsing cores. Each one of these cores is now its own separate entity, its own gravitational system, destined to become a new star or a small star cluster. Let's now zoom our focus in on just one of these collapsing cores. As the gas and dust in this core fall inwards under the pull of gravity,
they begin to pick up speed. And as the cloud gets smaller and denser, the particles start to bump into each other more and more often. This friction begins to generate heat. The core of the collapsing cloud starts to warm up. After tens of thousands of years of this slow, steady collapse, the center of the core becomes a hot, dense, and opaque ball of gas. It is no longer a transparent cloud, it is a glowing embryonic star. This is a protostar.
A protostar is, in essence, a stellar baby. It is a star in its earliest, most formative stage, and it's important to understand what it is and what it isn't. A protostar is hot and it is glowing. From a distance, it might even look like a real star, but it is not yet a true star. Its light and heat are not being generated by nuclear fusion in its core. Instead, its energy comes purely from the process of gravitational contraction. Think of it like this. As the gas and dust from the surrounding cloud continue to fall inwards onto the protostar, their gravitational potential energy is converted into thermal energy, into heat. It's the same principle as a meteorite hitting the Earth and creating a flash of light and heat. The protostar is constantly being bombarded by its own infalling material, and this is what makes it shine. It is powered by the quiet, relentless process of its own assembly. The protostar itself is hidden from our view. It is still shrouded deep within the dense, dark, dusty cloud from which it is being born. We cannot see it with visible light telescopes. But the heat it generates warms up the surrounding dust, and this dust then glows brightly in infrared light. So the James Webb Space Telescope, with its incredible infrared vision, is the perfect tool for peering into these stellar nurseries and seeing these embryonic stars for the very first time. It is giving us our first detailed baby pictures of other suns. Now, as this central protostar is forming, something beautiful and very important is happening to the rest of the material in the collapsing cloud. This brings us to the formation of the protoplanetary disk. As the initial, large, and very slowly rotating cloud of gas began to collapse, the law of conservation of angular momentum, the same law that makes an ice skater spin faster when they pull in their arms, caused the collapsing cloud to spin faster and faster. This rapid spin creates an outward centrifugal force, and this force prevents all the material from just falling directly onto the protostar at its center. Instead, the infalling gas and dust begin to flatten out into a vast, spinning, pancake-shaped disk around the central protostar. This is a protoplanetary disk, or as they are sometimes called, a proplide. It is, in essence, a solar system in waiting. This disk is a dynamic and fascinating place. It's a cosmic potter's wheel, a swirling vortex of the raw materials from which future planets, moons, asteroids, and comets will be built. The disk is not uniform. The inner part of the disk, closer to the hot, glowing protostar, is much hotter. Here, only materials with very high melting points, like rock and iron, can exist in solid form. The lighter, more volatile materials, like water ice and methane ice, are vaporized. Farther out in the disk, beyond a point called the frost line or snow line, it is cold enough for these ices to exist in their solid frozen state. This temperature difference in the disk is the fundamental reason why our own solar system is structured the way it is, with small, rocky planets on the inside and large, gassy and icy giants on the outside. For the next few million years, the protostar will continue to grow, feeding on a steady stream of material from this surrounding disk. But this is not a gentle, quiet process of feeding. The youth of a star, it turns out,
is a time of incredible violence and spectacular outbursts. This brings us to the next chaotic chapter in our story.
We often think of stars as calm, steady beacons of light. But their infancy is a messy, chaotic, and incredibly violent period. A young protostar, while it is still actively gathering mass from its surrounding disk, doesn't just pull material in, it also blasts a significant amount of material back out into space in the form of powerful, tightly focused jets. This is the phenomenon of bipolar jets. As the gas and dust from the protoplanetary disk swirls inwards towards the young star, it gets tangled up in the star's powerful and complex magnetic field. The magnetic field lines act like a cosmic centrifuge, grabbing some of this infalling material and flinging it outwards at incredible speeds. And because the star and the disk are rotating, these jets are funneled out along the star's north and south rotational poles. The result is two narrow, symmetrical beams of superheated plasma shooting out in opposite directions from the hidden protostar like a cosmic laser cannon. These jets are colossal. They can stretch for light years out into the surrounding molecular cloud. And they are moving at incredible speeds, hundreds of kilometers per second. We can't see the tiny protostar itself buried deep in its dusty cocoon, but we can see the dramatic effect that these powerful jets have on the surrounding environment. This brings us back to the beautiful phenomenon of Herbig-Haro objects. A Herbig-Haro object, as we've learned, is not a star, but a small, bright, and often beautifully shaped patch of glowing nebulosity. It is the impact zone. It is the place where one of these powerful, narrow protostellar jets is slamming into the cold, quiet gas of the surrounding molecular cloud.
Imagine a stream of water from a high-pressure hose hitting a wall of soft mud. The impact would create a messy, turbulent, and splattered pattern. A Herbig-Haro object is the cosmic equivalent of that. The jet acts like a powerful cosmic sandblaster, creating a brilliant and intricate shockwave that heats the hydrogen gas and causes it to glow. These objects are some of the most beautiful and dynamic sights in the night sky. They often have complex, bow-shock shapes, like the wake of a boat moving through water. And because the jets themselves are often clumpy and erratic, the Herbig-Haro objects can change their appearance noticeably in just a few years, a mere instant in astronomical time. By studying their shape and their motion, astronomers can learn a great deal about the hidden, newborn star that is creating them. They are a quiet, glowing fingerprint of a star's violent birth. After this initial, highly focused jet phase, which might last for a few 100,000 years, the young star enters a new phase of its youth. It is still not a true hydrogen-fusing star yet. It is still a protostar powered by gravitational contraction, but its outward expression changes. This is the T Tauri phase. A T Tauri star, named after the prototype star in the constellation Taurus, is a young star that is no longer shooting out those tight, narrow jets. Instead, it is producing a very strong, very chaotic, and very powerful stellar wind that flows outwards in all directions. This T Tauri wind is much, much stronger than the gentle solar wind that our own sun produces today. It is a furious, adolescent gale. And this powerful wind has a profound effect on the young star's environment. It begins to blow away the remaining gas and dust from the star's original cocoon.
This process is like a final great clearing of the fog. For millions of years, the protostar and its surrounding protoplanetary disk have been hidden from view, shrouded deep within their dark, dusty molecular cloud. But now, this powerful T-Towery wind acts like a giant celestial leaf blower, pushing away the remaining veils of gas and dust and revealing the young star and its brand new solar system to the universe for the very first time. This brings us to the final and most important act in the story of a star's birth. The star is now visible. It has stopped accreting most of its mass. It has cleared out its immediate neighborhood. It is still powered by the heat of its own gravitational collapse, but that process cannot last forever. The core of the star has been growing denser and hotter for millions of years, and it is now approaching the critical tipping point. We now arrive at the central moment of creation, the moment a glowing ball of gas becomes a true star, the birth of a sun. As the protostar continues to slowly contract under its own immense gravity, the pressure and the temperature at its very core continue to climb. The crush of gravity is relentless. The core becomes a crucible of almost unimaginable conditions. Finally, after millions of years of this slow, steady squeezing, the temperature at the very center of the protostar reaches a magic number, about 15 million degrees Celsius. At this incredible temperature, the hydrogen nuclei, which are just single protons, are moving so incredibly fast that they can finally overcome their natural electrical repulsion. Protons are both positively charged, and as you know, like charges repel, but in the heart of the protostar, the pressure is so great and the temperature so high that they are slammed together with enough force to allow a different, much more powerful force of nature to take over. This is the strong nuclear force, and it is at this moment that the universe's most powerful and most efficient engine turns on. This is the ignition of nuclear fusion.
Let's take a quiet moment to appreciate the beautiful process of hydrogen fusion, the engine that powers almost every star you can see in the night sky. The process in a star like our Sun is called the proton-proton chain. It happens in a few steps. First, two protons are slammed together with such force that one of them transforms into a neutron, releasing a couple of other small particles. The result is a nucleus of deuterium, or heavy hydrogen, which has one proton and one neutron. Next, this deuterium nucleus is hit by another proton, and they fuse together to form a nucleus of helium-3, which has two protons and one neutron. Finally, two of these helium-3 nuclei collide and fuse together. In this reaction, two of the protons are kicked out, and what is left behind is a single, very stable nucleus of helium-4, which has two protons and two neutrons. So the net result of this entire chain reaction is that four hydrogen nuclei have been converted into one helium nucleus. But here's the magic. If you were to take the mass of the final helium nucleus, you would find that it is slightly less massive than the four original hydrogen nuclei that you started with. About 0.7% of the original mass has disappeared. But it hasn't really disappeared. It has been converted directly into a tremendous amount of pure energy, according to Einstein's famous and beautiful equation, E equals mc squared. This release of energy from the fusion in the core creates a massive outward pressure. This new, powerful nuclear pressure pushes against the inward crush of gravity, and the star finds a new, long-term state of perfect equilibrium. The gravitational collapse stops. The star stops shrinking. It has become a stable, self-regulating, hydrogen-fusing main sequence star. It has truly been born.
This ignition of nuclear fusion is the single most important event in the life of a star. It is the moment it truly comes alive. The new, powerful outward pressure from the fusion in the core pushes against the inward crush of gravity, and the star achieves a new, long-term state of perfect balance called hydrostatic equilibrium. The gravitational collapse that defined its youth finally comes to a halt. The star stops shrinking. It has become a stable, self-regulating, hydrogen-fusing main sequence star. It has, after millions of years of quiet, patient gathering, finally been born. And the birth of this new sun has an immediate and dramatic effect on its surrounding environment. This brings us to the final act of this creation story, the emergence of a new solar system. For millions of years, while the protostar was slowly gathering mass, its protoplanetary disk was also quietly at work. In the swirling dust and gas of the disk, the process of planet formation has been underway. But this young solar system is still shrouded in a thick fog of leftover primordial gas. When the new star at the center ignites, it unleashes a much more powerful and consistent stellar wind than it had in its chaotic T-Tauri phase. This new, strong wind, along with the intense radiation from the star, acts like a colossal broom, sweeping through the entire system. It begins to blow away the last remnants of the gas from the protoplanetary disk. This is a quiet but dramatic clearing event. Over the next few million years, the hazy, nebulous fog that has enshrouded the young system is pushed out into interstellar space. And as this fog clears, the newly formed objects that have been quietly growing within the disk are revealed to the light for the very first time. What is left behind is a young, clean, and orderly solar system, a brilliant new star at the center, surrounded by a family of newly formed planets, asteroids, and comets, each one now set on its own stable, long-term orbit. The process of creation is complete.
So how do those planets actually form within that quiet spinning disk of gas and dust? The story of planet formation is another beautiful, slow, and sometimes violent tale of gravity and patience. The leading theory for how it happens is called the core accretion model. It begins in the protoplanetary disk with the tiniest of objects, microscopic grains of dust. These are the particles of silicate and carbon that were forged in previous generations of stars. In the cold, quiet disk, these dust grains begin to stick together. At first, the force holding them together isn't gravity, but simple static electricity, like dust bunnies forming under your bed. They form small, fluffy aggregates. As these fluffy aggregates drift through the disk, they bump into each other and stick together, growing larger and larger. Once they reach a size of about 1 kilometer across, they are called planetesimals. And at this size, their own collective gravity becomes strong enough to start influencing their neighbors. They are now no longer just passively sticking together. They are actively, gravitationally pulling in other smaller objects. This begins a long period of hierarchical growth. The larger planetesimals, with their stronger gravity, grow the fastest. They sweep up all the smaller material in their orbital path, cleaning out their neighborhood. This process is a bit like a cosmic snowball rolling downhill, getting bigger and bigger as it picks up more snow. Over millions of years, these planetesimals will collide and merge, growing from kilometer-sized objects to moon-sized objects, and finally to the large protoplanets that will become the cores of future worlds. The entire process is a quiet, slow, and patient game of gravitational billiards.
The type of planet that forms depends entirely on where in the disk it is born. This brings us back to the concept of the frost line or snow line. As we discussed, the inner part of the protoplanetary disk, being closer to the hot, glowing protostar, is much warmer. The outer part of the disk is much, much colder. The frost line is the specific distance from the central star where it is cold enough for volatile compounds like water, ammonia, and methane to freeze into solid ice grains. In the inner part of the disk, inside the frost line, it is too hot for these ices to exist. The only solid materials available to build planets are the less abundant, heavier elements like iron, silicon, and magnesium. So the planets that form here are the small, dense, rocky planets. They grow from the slow accretion of these rocky and metallic planetesimals. Because rock and metal are relatively rare ingredients in the cosmic recipe, these planets never get a chance to grow truly massive. This is why our own inner solar system is home to the 4 small rocky worlds: Mercury, Venus, Earth, and Mars. But in the outer part of the disk, beyond the frost line, the story is completely different. Here, it is cold enough for water ice to be a solid building material. And in the early solar nebula, there was far more water ice available than there was rock and metal. This meant that the protoplanets that formed in the outer solar system could grow much, much larger and much more quickly. They had access to a much larger reservoir of solid material. And once a protoplanet's core reached a certain mass, about 10 times the mass of the Earth, something spectacular happened.
Once the core of a protoplanet in the outer solar system reached this critical mass of about 10 Earth masses, its gravity became so powerful that it was able to do something the smaller, rocky inner planets could not. It was now strong enough to directly capture and hold on to the vast amounts of light, primordial gas from the surrounding nebula, primarily hydrogen and helium. This triggered a period of runaway growth. The protoplanet began to rapidly accrete a huge, thick, gassy atmosphere around its solid, icy, or rocky core. Over a few million years, it would grow from a super-Earth-sized core into a true colossus, a gas giant like Jupiter or an ice giant like Neptune. This is why the outer solar system is home to these massive, low-density worlds. They were born in a region where they had access to not just rock, but the much more abundant building material of ice, which allowed them to grow large enough to capture their huge gassy envelopes. This entire process of planet formation, from tiny dust grains to giant planets, takes place over a period of a few million to perhaps 10 million years, all happening quietly within the protoplanetary disk while the central star is still in its protostar phase. By the time the star finally ignites and its solar wind blows away the remaining gas, the main construction of the solar system is already complete. What is left is a young and still somewhat chaotic family of new worlds. The final stage is a long, quiet cleanup phase lasting for another few 100 million years. During this time, the newly formed planets continue to gravitationally interact with each other and with the remaining leftover planetesimals, settling into their final stable orbits. This is often a violent period, the late heavy bombardment we have talked about before, where the young planets are constantly being peppered by the remaining debris. But eventually, this too subsides, leaving behind a calm, orderly, and mature solar system, a quiet testament to a long and chaotic birth.
And so we have followed the beautiful, quiet story of the birth of a single sun-like star and its family of planets. But our sun is just one of billions of stars in our galaxy, and it is just one of many different types. The same basic process of gravitational collapse that we have described can create a wonderfully diverse zoo of different stellar objects, depending on the initial mass and conditions of the primordial cloud. For this next part of our journey, let's take a quiet look at some of these other stellar siblings. We'll begin with the most common and most long-lived type of star in the entire universe. We are at level 29 again, but for a much deeper dive, the red dwarfs. When we look up at the night sky, all the stars we see with our naked eye are much larger and much brighter than our own sun. This gives us a very biased view of the stellar population. The quiet truth is that the vast, overwhelming majority of stars in our galaxy, perhaps as many as 75% of them, are small, cool, and incredibly dim red dwarfs. They are the quiet, unassuming citizens of the cosmic city. A typical red dwarf might have anywhere from about 8% to about 50% of the mass of our Sun. Because they are so much less massive, the gravitational pressure in their cores is much lower. This means they burn through their hydrogen fuel at a much slower rate than a star like our Sun. They are incredibly fuel efficient. They sip their fuel rather than gulping it. And this leads to their most remarkable feature: their almost unbelievably long lifespans. A star like our Sun will live for about 10 billion years. A red dwarf star can live for trillions of years. Some of the smallest ones have a theoretical lifespan that is longer than the current age of the universe by a factor of hundreds. This means that not a single red dwarf that has ever been born in the entire 13.8 billion year history of the cosmos has had enough time to die yet. Every single one of them is still in its stellar infancy, quietly fusing hydrogen, and will continue to do so for trillions of years to come, long after every other star in the universe has gone dark.
The incredible longevity of red dwarfs makes them very interesting places to consider in the search for life. While they have their challenges, they are dim, so their habitable zones are very close, and they can be very volatile and prone to flares in their youth. They also offer the one thing that complex life might need most of all: time. An almost infinite amount of quiet, stable time for life to arise and to evolve. Now let's look at the other end of the stellar spectrum. Let's explore the lives of the blue giants, the massive, hot, and spectacular rock stars of the galactic neighborhood. These are the O-type and B-type stars, and they are the complete opposite of the quiet, patient red dwarfs. These stars are born from the most massive cores in a molecular cloud. They can have anywhere from 10 to over 100 times the mass of our Sun. And because they are so massive, the gravitational pressure in their cores is immense. This causes them to burn through their hydrogen fuel at a furious, almost obscenely profligate rate. A star that is 50 times as massive as our Sun can be hundreds of thousands or even millions of times more luminous. They are brilliant, dazzling beacons of blue-white light. But this incredible brilliance comes at a cost. They live very, very fast, and they die very, very young. The lifespan of a massive blue giant might only be a few million years. It is a cosmic blink of an eye. For this reason, we only ever find them in the spiral arms of galaxies, the regions of active star formation. They simply do not live long enough to drift away from the stellar nursery where they were born. And their deaths are as spectacular as their lives. As we know, these are the stars that die in massive supernova explosions, creating the neutron stars and black holes that we have talked about. And it is in their fiery hearts and their explosive deaths that all the heavy elements needed for life are created and scattered throughout the galaxy.
So while they are rare and short-lived, these brilliant, beautiful, and violent stars are essential for the story of cosmic creation.
Now, let's consider another very common arrangement that we often overlook. This is the reality of binary and multiple star systems. When we look up at the night sky, we see single points of light, and our own solar system has a single, stable sun at its center. So we tend to think of this as being the normal state of affairs. But the quiet truth is that our solitary sun is actually in the minority. The process of a giant molecular cloud collapsing and fragmenting is a messy and chaotic one. It's very common for two or more protostars to form very close to each other, becoming gravitationally bound from the very beginning. The result is that more than half of all sun-like stars and an even higher percentage of massive stars are not single stars, but are part of a binary or multiple star system. They are cosmic siblings, locked in a gravitational dance that will last for their entire lives. These systems can be incredibly diverse. You can have two sun-like stars orbiting each other in a close, intimate waltz. You can have a massive blue giant orbiting with a smaller red dwarf companion. You can have complex triple or even quadruple star systems, with stars orbiting other stars, which are in turn orbiting the system's common center of mass. The existence of these systems has profound implications for planet formation. For a long time, astronomers thought it would be very difficult for stable planets to form in a binary star system. The complex, shifting gravity of two suns, they thought, would likely eject any forming planets from the system. But we are now discovering that this is not the case. We have found planets that orbit just one of the stars in a close binary pair, and we have even found circumbinary planets, like Kepler's 16b, which orbit both stars at once in a wide, stable orbit. The quiet truth is that a sky with two suns might be just as common or even more common than a sky with one.
Finally, in our tour of stellar diversity, let's return to the objects that don't quite make the cut. Let's spend a little more quiet time with the brown dwarfs, the failed stars. These objects occupy the fascinating, blurry line between a giant planet and a small star. They form in the same way as stars, from the gravitational collapse of a clump of gas in a molecular cloud. But they are the runts of the litter. They just don't manage to accrete enough mass to get hot and dense enough in their cores to ignite sustained hydrogen fusion. The dividing line is about 80 times the mass of Jupiter. Anything more massive than that, and it becomes a red dwarf. Anything less, and it becomes a brown dwarf. So what are they like? They are not quite stars and not quite planets. They are sometimes called substellar objects. They are hot when they are young, glowing with a faint, deep reddish magenta light from the residual heat of their formation. But they have no internal engine. So, as they age, they just slowly, quietly cool down and fade away, eventually becoming dark, invisible objects, not so different from a rogue gas giant planet. Because they are so dim and cool, they are incredibly difficult to find. We have only been discovering them in large numbers in the last couple of decades, thanks to sensitive infrared telescopes that can detect their faint heat. And what we are finding is that they are very common. There may be as many brown dwarfs in our galaxy as there are normal stars. The space between the stars might be filled with these quiet, warm, and lonely failed suns.
They are the most populous members of our galaxy that we cannot see with our own eyes. A vast, hidden population of cosmic almosts.
Our final stop in this gallery of stellar diversity brings us back to the most common arrangement of all. While we are used to our solitary sun, the quiet truth is that most stars, especially the larger ones, are not born alone. They are born as binary or multiple star systems. The same chaotic, turbulent process that causes a giant molecular cloud to fragment into dozens of individual star-forming cores can also cause those cores themselves to be very close together, or even to fragment further as they collapse. The result is that it's very common for two or more protostars to form in a shared gravitational embrace, locked in a dance around a common center of mass from the very beginning. These systems are a universe of variety in themselves. You can have wide binaries, where two stars orbit each other at a great distance, thousands of times farther apart than the Earth is from the Sun. In these systems, each star could likely have its own stable family of planets, and the companion star would just look like an incredibly bright but distant star in the night sky. But you can also have close binaries, where the two stars orbit each other at a distance similar to our own planets, or even closer. In these dynamic and chaotic systems, the gravitational environment is much more complex. The stars can exchange mass, as we saw in the Algol paradox, dramatically altering their evolution, and the process of planet formation becomes much more strange and wonderful. The protoplanetary disk in such a system wouldn't be a simple, flat pancake around a single star. It could be two separate disks, one around each star. Or it could be a single large circumbinary disk that surrounds both stars at once, like a giant spinning cosmic donut. For a long time, astronomers thought that the complex, shifting gravity in these close binary systems would make it impossible for stable planets to form. But our new telescopes are proving that assumption to be wrong.
We are now discovering a whole zoo of strange and wonderful planets in binary star systems. We have found Tatooine worlds like Kepler's 16b that orbit both stars at once, enjoying the light and warmth of two suns in their sky. And we have found planets that orbit just one of the two stars, with the other star appearing as a brilliant second sun in their sky, sometimes closer, sometimes farther away, depending on the orbits. The quiet truth is that a sky with two suns might be more common in our galaxy than a sky with one. It's a beautiful and humbling thought that our own single-star system might be the unusual one, a quiet exception to the more common rule of stellar companionship. This idea of binary formation, of shared birth, is a fundamental part of the story of how stars are made. And with that, we conclude our tour of the diverse types of stars that can be born. We have seen the long-lived, quiet red dwarfs, the brilliant and fleeting blue giants, the strange, failed brown dwarfs, and the common, companionate binary systems. But how do we know all of this? How do we see into these dark, dusty nurseries and witness these events from so far away? This brings us to our next great chapter. For most of human history, the birth of a star was a complete mystery, an event that was completely invisible to us. The stellar nurseries where they are born are shrouded in thick, dark clouds of dust that block all visible light. It's like trying to watch a baby grow inside a locked room with no windows. But in the last century, we have developed new kinds of eyes, new kinds of telescopes
that can peer through that dusty veil and see the quiet, beautiful process of creation happening within. Let's take a quiet tour of the tools that have allowed us to tell this story.
Our journey begins not with light we can see, but with a kind of light that is much longer and much less energetic. We start with radio telescopes. The giant molecular clouds where stars are born are incredibly cold. And because they are so cold, they don't glow in visible light. They are dark. But they do emit very faint radiation at very long wavelengths in the radio and microwave part of the spectrum. To see the very first stages of star formation, we need radio telescopes. These are not the familiar telescopes with mirrors and lenses. They are giant, curved dishes, sometimes acting alone, sometimes linked together in vast arrays that can stretch for miles. They act like giant, sensitive ears, listening for the faint, cold whispers of the cosmos. One of the most powerful of these is the Atacama Large Millimeter Submillimeter Array, or ALMA, located high in the desert mountains of Chile. ALMA is an array of 66 massive radio dishes that can be moved around and linked together to act as a single, giant, planet-sized telescope. By looking at the faint millimeter wavelength light emitted by the cold dust and molecular gas, ALMA can peer deep inside the dark stellar nurseries. It can see the dense, cold cores that are just beginning to collapse, even before a protostar has formed. It can map the structure of the swirling protoplanetary disks around the young embryonic stars. It can even see the gaps in those disks that are being carved out by newly forming, invisible planets. Radio telescopes like ALMA are our eyes on the very first, quietest, and coldest stages of starbirth. They allow us to see the seeds before they have even begun to sprout.
While radio telescopes show us the cold, dark beginnings, our next tool shows us the beautiful, glowing artwork that starbirth creates. This, of course, is the Hubble Space Telescope. For over 30 years, Hubble has been our premier eye on the universe in visible light. And while visible light cannot penetrate the densest parts of a stellar nursery, it can give us a spectacular view of the effects of starbirth on the surrounding cloud. Many of the most famous and beautiful astronomical images ever taken are Hubble's portraits of stellar nurseries. Let's return to the pillars of creation in the Eagle Nebula. The Hubble image shows us the grand structure of these colossal pillars of gas and dust. But what it shows us most beautifully is the process of photoevaporation. We can see the brilliant, hot young stars that have already formed just above the pillars. And we can see how their intense, energetic radiation is sculpting the pillars, boiling away their surfaces and creating the beautiful, glowing, hazy edges. Hubble also gave us our first clear views of the protostellar jets we discussed earlier. In its images, we can see these thin, laser-like beams shooting out from hidden young stars and slamming into the surrounding gas, creating the beautiful glowing shockwaves of the Herbig-Haro objects. And Hubble, by looking at the Orion Nebula, gave us our first direct visual evidence of protoplanetary disks around young stars. It captured stunning, iconic images of these proplids, seen as dark, silhouetted disks against the bright, glowing gas of the nebula behind them. Hubble showed us in breathtaking detail the environment of a stellar nursery. It showed us the art, the chaos, and the incredible beauty of a galaxy in the act of creation. It showed us the cradle. But to see the baby sleeping inside, we would need a new kind of eye.
And that new eye, as we know,
is the James Webb Space Telescope. If radio telescopes see the cold initial cloud, and Hubble sees the beautiful visible light effects on the outside of the cloud, then the JWST is the machine that can finally peer through the dusty curtains and see the main event happening inside. As we've discussed, Webb is an infrared telescope. An infrared light has a longer wavelength than visible light, which means it can pass much more easily through clouds of interstellar dust without being scattered. This gives Webb a kind of superpower, the ability to see the invisible. When Webb looks at a dark, dusty stellar nursery like the pillars of creation, the dust that was opaque to Hubble becomes a sheer translucent veil. And through that veil, Webb can see the hundreds of tiny red newborn protostars that were hidden inside. It can see the glowing knots of gas where stars are still in the process of being born. It can see the intricate details of the protostellar jets shooting out from these infant suns. It is giving us our first clear, direct look at the process of star birth as it is happening. Let's take another example, the cosmic cliffs in the Carina Nebula. The Webb image of this region is one of the most beautiful scientific images ever created. It shows a vast landscape of orange and brown mountains of gas being carved away by the radiation from nearby massive stars. And deep within these gaseous mountains, Webb's infrared eye has revealed hundreds of previously unseen protostars, like tiny hidden jewels embedded in the rock. It can even see the bubbles and cavities being created by the jets from these newborn stars as they begin to blow away their own dusty cocoons. The James Webb Space Telescope is not just taking pictures, it is pulling back the final curtain on the quiet, hidden, and deeply beautiful process of stellar creation.
Now that we have seen the tools we use to understand star birth, let's take a quiet journey through the history of the idea itself. How did we as a species come to understand where stars come from? This brings us to the history of our understanding. For most of human history, the stars were seen as eternal, unchanging, perfect points of light, perhaps holes in a celestial sphere or the campfires of the gods. The idea that stars were physical objects that had a birth, a life, and a death was not a part of our worldview. The first quiet hints of a scientific theory of star formation began to emerge in the 18th century, during the Age of Enlightenment. Philosophers and scientists, armed with the new physics of Isaac Newton, began to think of the universe as a grand mechanical clockwork. The great German philosopher Immanuel Kant in 1755 was one of the first to propose that nebulae, the fuzzy clouds seen in early telescopes, might be regions where new stars and planets were forming from a collapsing cloud of gas under the influence of gravity. A similar idea was proposed independently a few decades later by the French mathematician Pierre-Simon Laplace. This nebular hypothesis was a brilliant piece of intuition, and it is the direct ancestor of our modern theory. But for the next century and a half, it remained just that, a hypothesis, a philosophical idea with little observational evidence to support it. The true breakthrough in understanding how stars work had to wait until the early 20th century and the dawn of nuclear physics.
It was then that scientists like Arthur Eddington first proposed that the source of a star's immense power was the fusion of hydrogen into helium in its core. This understanding of the stellar engine was the key that finally allowed us to build a detailed physical model of a star's entire life story.
The middle of the 20th century saw the next great leap in our understanding. With the development of radio astronomy, we were able to peer into the cold, dark molecular clouds for the first time and see the raw material for star formation. And as our understanding of nuclear physics grew, scientists were able to create detailed models of how a collapsing cloud of gas could heat up and eventually ignite this fusion engine. But the real revolution has happened in just the last few decades, with the rise of two powerful new tools: space telescopes and supercomputers. Space telescopes, like Hubble and now Webb, have given us our first clear, detailed images of these stellar nurseries, allowing us to see the different stages of starbirth in action. We are no longer just theorizing, we are observing. And at the same time, the incredible power of modern supercomputers has allowed us to create detailed, complex simulations of the star formation process. We can create a virtual molecular cloud in a computer, apply the laws of physics, and watch as it collapses, fragments, and forms a cluster of virtual protostars, each with its own disk and jets. We can then compare these simulations to the real images from our telescopes, to test our theories and refine our understanding. This quiet, powerful combination of observation and simulation has, in just the last few years, given us an incredibly detailed and beautiful picture of how stars are born. It is a story that began as a philosophical speculation 2 centuries ago and has now become one of the most successful and well-tested theories in all of modern astronomy. And now, let's take all of this knowledge and apply it to the most important star in our lives. Let's tell the quiet, specific story of the birth of our own sun.
We have explored the general process of star formation, but what about our own sun? Can we piece together the specific details of its birth some 4.6 billion years ago? The answer, through a clever form of cosmic archaeology, is yes. The story of our sun's birth is written in the very rocks of our solar system. Our story begins in a vast, cold, giant molecular cloud, much like the ones we've discussed. We don't know exactly where it was, but it was somewhere in a now forgotten spiral arm of the young Milky Way galaxy. Within this cloud, a specific, dense core of gas and dust began to collapse. This was the parent molecular cloud that would become our home. What triggered this collapse? We have a very strong clue, and it is a quiet, radioactive one. When we analyze the composition of the oldest meteorites in our solar system, which are pristine, leftover building materials from that time, we find an unusually high concentration of a specific isotope of iron called iron-60. Iron-60 is a radioactive element that is only produced in one place, the heart of a massive star, right before it explodes as a supernova. And it has a relatively short half-life, which means it must have been created very shortly before our own solar system formed. This is our smoking gun. The most likely story is that the collapse of our own solar nebula was triggered by the shockwave from a nearby supernova. A massive neighboring star lived its short life and then died in a colossal explosion. The shockwave from this explosion slammed into our quiet, stable cloud, compressing it and triggering its collapse. And at the same time, it seeded our young solar system with a fresh batch of heavy elements, including the very iron that makes up the core of our planet and the blood in our veins. Our sun was likely born from the violent death of another, older star.
So, with this supernova trigger, our own small patch of the molecular cloud began its slow, quiet collapse. Over the next few 100,000 years, it formed a spinning central protostar, the young sun, surrounded by a vast, flat, rotating protoplanetary disk. This disk was the birthplace of all the planets. And as we've learned, the composition of this disk was not uniform. There was a frost line. In our own solar system, the frost line was located somewhere in what is now the main asteroid belt between the orbits of Mars and Jupiter. Inside this line, it was too warm for water ice to exist in solid form. The only solid materials available were the less abundant rock and metal. And it was from this rocky metallic dust that the four inner terrestrial planets, Mercury, Venus, Earth, and Mars, were slowly built through the process of accretion. Outside the frost line, the story was very different. It was cold enough for water ice to be a solid, and water ice was a much more abundant building material than rock. This allowed the cores of the planets in the outer solar system to grow much larger, much more quickly. Jupiter and Saturn grew so massive, to over 10 times the mass of the Earth, that their powerful gravity was able to pull in huge amounts of the primordial hydrogen and helium gas from the surrounding nebula, turning them into the gas giants we see today. Farther out still, Uranus and Neptune also grew large cores of rock and ice, but by the time they had formed, much of the gas in the nebula had already been blown away, so they ended up with much thinner atmospheres, becoming the ice giants. This simple temperature gradient in our own protoplanetary disk is the quiet, fundamental reason for the beautiful, orderly architecture of our solar system, with its small, rocky worlds on the inside and its large, gassy and icy worlds on the outside.
While the planets were quietly forming in the disk, our young sun was going through its chaotic, adolescent T-Tauri phase. For a few million years, it would have been blasting the inner solar system with a stellar wind far more powerful than the one it has today. This powerful wind is what eventually cleared out the remaining gas and dust from the solar system, revealing the newly formed planets. Finally, after about 50 million years of this slow contraction, the pressure and temperature at the center of the young sun reached that magic number of 15 million degrees. Nuclear fusion ignited in its core. Its gravitational collapse stopped. It became a stable main sequence star. Our sun was born. The solar system it illuminated, however, was still a very violent and chaotic place. The final stage was the great cleanup phase, the late heavy bombardment. The young solar system was still filled with a huge number of leftover planetesimals and comets. For the next few 100 million years, these objects would constantly be crashing into the newly formed planets, including our own Earth. This was the era that created the vast cratered landscapes we see on the Moon. It was a time of immense planet-shaping violence. But this violent bombardment was also, paradoxically, a life-giving event. It is thought that these comets and asteroids, which were rich in water and organic molecules, were responsible for delivering a significant portion of the water that now fills our oceans and the chemical building blocks that would be needed for life to arise. And so, after about 1 billion years of this chaotic formation and violent cleanup, our solar system finally settled down into the calm, orderly, and relatively peaceful neighborhood that we know today. It is a quiet, beautiful, and deeply complex story of creation. A story that took place over hundreds of millions of years, all to create the one star and the one small blue planet that we call home.
And so,
Our long and quiet journey into the heart of a stellar nursery comes to its gentle close. We have traveled from a vast, cold, dark, and almost perfectly empty cloud of molecular gas, and we have witnessed its slow, patient transformation into a brilliant, shining star. We have explored the quiet triggers that can start this process, the gentle nudge from a spiral arm or the violent shove from a nearby supernova. We have watched as the cloud collapsed under its own gravity, fragmenting into the dense cores that would become the seeds of new suns. We have peered through the dust and seen the faint, warm glow of a protostar, an embryonic sun powered not by fusion but by the simple heat of its own contraction. We have marveled at the beautiful spinning protoplanetary disk that forms around this young star, the cosmic potter's wheel from which new worlds are sculpted. And we have witnessed the star's chaotic and violent youth, a time of powerful jets and furious winds that both build and destroy the environment around it. And finally, we have arrived at that single, magic moment of ignition, when the pressure and temperature in the core reach the critical point, and the quiet, steady, life-giving fire of nuclear fusion begins, a fire that will burn for billions of years. The story of how a star is born is one of the most fundamental and most beautiful stories in all of science. And it is, at its heart, a story of balance. It is a story of the delicate cosmic dance between the relentless inward pull of gravity and the powerful outward push of pressure and heat. It is this quiet, perfect equilibrium that defines a star for its entire life.
The story of star birth is also a profound story of recycling. The universe is incredibly efficient. Nothing is ever truly wasted. The very giant molecular cloud that we started our journey in was itself made of materials that were created in a previous generation of stars. The hydrogen and helium were from the Big Bang, yes, but the tiny crucial grains of dust, the carbon, the oxygen, the silicon, were all forged in the fiery hearts of massive stars that lived and died long before our own sun was ever born. And the new star that is created will, in turn, continue this cycle. A star like our sun, at the end of its life, will puff its outer layers back out into space, enriching the interstellar medium with new heavy elements. And a massive star will die in a supernova explosion that seeds the entire galaxy with the building blocks for new stars, new planets, and new life. It is a quiet, endless, and beautiful cycle of birth, death, and rebirth. The very atoms that make up our planet and our own bodies were once part of one of these vast, cold molecular clouds, and before that, they were forged in the core of an ancient, long-dead star. We are, in the most literal sense, made of stardust. We are the children of this grand cosmic recycling program. So as you drift off to sleep tonight, let your mind be at peace with this thought. Think of those quiet, dark, and cold clouds drifting silently between the stars, and think of the incredible, patient, and beautiful process that is happening inside them right now. All across our galaxy, new suns are being born, new solar systems are taking shape, and new worlds are being created. The quiet story of creation is not just a story of the past, it is a story that is happening all around us, all the time. It is the gentle, steady heartbeat of our living universe.